In the last session, we have discussed up to the diagonal matrices under the types of matrices. And today I will start the session from the starting discussion for identity matrix. Uh, an identity matrix is said to be again a square matrix having the special property that um, can we say that the identity matrix is a square matrix as well as a diagonal matrix. The special property of the identity matrix is we can see ones in the main diagonals and all the other elements are become zeros. Therefore, if we can say the identity matrix, we are generally denoting it as the using the uppercase letter I, and here we are just writing the order of the matrix or the dimension of the matrix as n. It is because I told you that identity matrix is always a square matrix. Therefore, it is no need to write this as n by n. This can be directly write down as I with this n. It is because we know that if you have write it in this form, we know that I stands for the identity matrix and n stands for the dimension of the matrix. Since we know the number of rows, then it would be equal to the number of columns at that matrix. That is why we can replace it using in. Then if you consider any identity matrix, it would be an square matrix and diagonal matrix itself. Actually, the identity matrix is a special case of diagonal matrices. It is because we can see only ones in the main diagonals and all the other elements are becoming zeros. Here I have mentioned down some identity matrix. Here we can see that it is a 1 by 1 matrix. Since it is 1 by 1, we can just say it as an integer only. And if you move for the next one, here we can see it as I2. Here we can see this as I2. I2 in the sense this is an identity matrix having the order as 2. It means that 2 rows are there and 2 columns are there. Now you can see that 2 rows and 2 columns are there, and you can see that all these off diagonal elements or only the elements in the main diagonals are ones. Apart from that, all the other elements are zeros. In here, this concept has extended for n number of rows and n number of columns. Here we can see that if you are running from the diagonal, running from the upper left to the bottom right, then you can see that all the elements on the main diagonals are ones and all other values or the elements are zeros. Therefore, if you can see a matrix in this form, then we are saying such matrix as an identity matrix. Now we will move for the next type of matrices. This is said to be the equal matrices. Actually, rather than saying this as a type of matrices, actually this is a valuable concept that we have to follow when we are discussing with matrices. If you are considering any two given matrices, if you are suppose that you are having any two matrices, and if you need to check whether these two matrices are equal matrices, but at the very beginning you may not feel that. Suppose that it is quite like this. Suppose this matrix A is 1 4 3 2, and I'm taking another matrix as matrix B. Matrix B as again is 1 4 3 2. You may feel that why we need to have this as A and B separately. It is because you can see that all these elements are same. And simply we can say that all these two matrices are same or similar matrices. Therefore, but when we are using these matrices in calculation, we have to follow these equal matrices. It is because for some proofs, we need to use this concept of equal matrices. Actually, rather than just using the numbers on two matrices and saying them as equal matrices, we tend to use the variables or just the unknown terms inside the matrices, and to calculate those values we can use the concept of equal matrices. And if you see about the conditions which should be satisfied to be equal matrices, there are three conditions which should be satisfied. First condition is the number of rows should be equal. It should be, it is for all these two, or for both these two matrices, they should be have with same number of columns, same number of rows. The second condition is the matrices should have same number of columns. Therefore, here also we can see that this is a 2 by 2 matrices, 2 rows, and here also we can see that 2 rows are there. Here we are having 2 columns. Here also we can see that there are 2 columns in the matrix B. Therefore, matrix A has 2 rows and 2 columns. Matrix B has 2 rows and 2 columns. Now you can see that first two conditions are satisfied. When we discuss about the equal matrices, we cannot say that the elements in the matrices are equal. It cannot be completed in that way. If we are having two equal matrices, then the corresponding elements should be equal. That is the thing which we need to check. We have to check for the corresponding elements. It means that the element in first row, first column should be corresponds to the element in first row, first column in the next matrix as well. Therefore, if you need to check for the matrices whether they are equal or not, after satisfying the first two conditions, then you have to check for the corresponding elements. It means that corresponding elements means if you consider the place that the element lies on, then the elements on those places should be same if the matrices are said to be equal matrices. Therefore, it is quite a scenario like this. Suppose that you are having matrix A. I am saying that matrix A is 1, 3, 4, 2. I am saying another matrix. I am taking matrix B. I am taking matrix B as 3, 1, 4, 2. If I consider these two matrices, you can see that this has 2 rows with 2 columns. This also having 2 rows with 2 columns. Now you can see that there are 2 rows, means number of rows are equal. Here we can see that both matrices consist of 2 columns. It means that the second condition satisfied, and simply same number of columns are there. And if you check for the third condition, as soon as you see these two matrices, you can see that elements are equal. It is because you can see that 1, 3, 4, and 2 are included in matrix A. And if you see for the matrix B, here also you can see that 1, 3, 4, and 2 are included, but the order is not similar. That is why that is the thing we need to check. We need to check not only the elements, but their order as well. We have to check. That is what is meant as the corresponding element. Even though we can see the equal elements inside these two matrices, we cannot say that these are equal matrices. And simply we can say that matrix A is not equal to matrix B. It is because if you see for these instances, now think about these places. In here, the first row, first element is 1. But in this matrix, first row, first column element is 3. Now you can see that these are not, or the corresponding elements are not equal or not similar. Therefore, we cannot say that these are two equal matrices. Therefore, if the matrices are said to be equal matrices, then the corresponding elements should be equal. If you consider this example, you can see that 1 is here, again 1 is here. The corresponding element are equal. Here also, if you consider this one, here 3 with 3, then 4 with 4, and here it is 2 with 2. Now you can see that elements in all the places of these matrices are similar. It means that it satisfies the condition corresponding elements are equal. Therefore, this is actually what we need to check if two matrices are said to be equal matrices. In this example also it is considered X is taken as a matrix having the elements A, B, C and D. Y has taken as a matrix having the elements P, Q, R and S. Here we can see that two rows are in both matrices. First condition satisfied. Two columns included in both matrices. It means second condition satisfied. Then to check for the third condition, or if this condition satisfy, we can say that matrices are equal matrices. Therefore, if you need that x and y are to be equal matrices, then A should be equal to P, B should be equal to Q, C should be equal to R, and D should be equal to S. Therefore, if these equalities satisfies, then since along with these first two conditions satisfying, then we can say that x and y are equal matrices. We are representing it using x equals y. Here this says that is x equals y. Therefore, we are using the equal notation to show that the matrices are equal each other. Then we will move for the next part under this matrices. Here we will discuss about the matrix operation. Under the matrix operations, first we will discuss for the addition of matrices. When we are looking about the addition of matrices, we cannot select any arbitrary matrix, any two arbitrary matrix and go for the matrix addition. If you need to add any two matrices, first there is a condition which should be satisfied. If that condition satisfied, then we are saying that those two matrices are confirmable for matrix addition. The condition which should be satisfied for matrix addition is the two considered matrices are should be in the same order, or simply we can say that if the dimensions of the matrices are same or equal, then we are saying that those matrices are confirmable for matrix addition. It is the first condition that should be satisfied. If that condition satisfying, then we can go for the addition of the two matrices. To consider or to have the addition of two matrices, what we need to do is we need to add the corresponding elements. Once the condition satisfying, then we need to add or sum up the corresponding elements to get an addition of matrices. Here I have included some examples. The first example is A having a matrix having elements 2, 4, 1 and 3, and B is a matrix having elements 3, 2, 1 and 0. Suppose that you are asked to find the value for A plus B. It is the addition of two matrices. First, you need to check whether the matrices are in the same order or not. According to this given information, we can see that A is a matrix having the order 2 by 2, or the dimensions 2 by 2. Matrix B is also having the order 2 by 2. Now, if you go for the addition of these two matrices, you can see that once you add these two matrices, then you can they are in the same order. Since they are in the same order, those matrices are said to be confirmable for matrix addition. Once the matrices are confirmable for matrix addition, then what we can do is we can add the corresponding elements. If you add the corresponding elements, you can add 2 with 3, 4 with 2, 1 with 1, and 3 with 0. Here you can see the added elements together, and you can see that the final answer is given as 5, 6, 2, 3, having the matrix with order 2 by 2. Therefore, if you add any two matrices which are confirmable for matrix addition, you will get the order of the resultant matrix as the order of the initial matrix which you have considered for the matrix addition. Therefore, here you can see that initial matrices are having the order 2 by 2, and here as well 2 by 2. Then the resultant matrix is also having the order 2 by 2. Then in the second example, you can see that a matrix having the order 2 by 4 has considered as A, having the elements 2, 4, 3, minus 4, 1, 2, 5, and 0 as elements. And here I am saying this as the matrix B. Actually, the letter is missing here. We have to name this as letter the matrix B. Here also we can see that this matrix having the matrix dimension as 2 by 4, 2 rows with 4 columns. And if you ask to find out the value for A plus B, first you need to check whether the matrices are conformable for matrix addition. It means that you need to check whether the dimensions of these two matrices are same or not. If you check for the condition, you can see that matrix A has 2 rows and 4 columns. It is a 2 by 4 matrix. Matrix B also having 2 rows with 4 columns. Means that again these two matrices are in same order. Since the condition satisfies, since the first condition satisfies, then you can add the corresponding elements. Therefore, the adding the corresponding element results this answer. It is 3, 5, 5, 3, 6, minus 4, 8, and 1, having the order as 2 by 4. It means 2 rows and 4 columns. Now, if you look about the order of the resultant matrix, it is similar as the initial matrices mentioned in the calculation. Therefore, if you are adding any two given matrices which are conformable for matrix addition, then we can say that the order of the resultant matrix is same as the order of the initial matrices. Then if you consider on this example here, matrix A is given as a 2 by 3 matrix and matrix B is given as a 3 by 3 matrix. If you ask to add these two matrices or perform the matrix addition among these two matrices, first you have to check whether the initial condition, whether they are in same order. As soon as you see these two matrices here, you can see that matrix A is having the order as 2 by 2, but matrix B is having the order 2. Matrix A is having the order as 2 by 3 and matrix B is having the order as 3 by 3. Therefore, you can say that the order of matrix A is not equal to the order of matrix B. Therefore, we cannot perform this matrix addition. It is because you can see that these two matrices are not conformable for matrix additions. Then we will move for the next one. It is the subtraction of matrices. When we are going for the looking for the matrix subtraction, here also we need to check for the condition which we have checked previously as whether the matrices are conformable for matrix subtraction. Here what we need to do is we need to check whether the given matrices are in same order or not. If the matrices are in same order, then we can say that the matrices are conformable for matrix subtraction. If the condition is satisfying, then we can go for the subtraction of the corresponding elements. And if I quickly go to the previous one, here we can see that simply in the algebra we know that 2 plus 3 is equal to 3 plus 2. Therefore, this rule is valid for matrices as well. If you are having matrix A with matrix B, and if you perform the addition among these two matrices, this will be equal to the matrix addition of B and A as well. Therefore, if you add A and B, this should be equal to the addition of B plus A. Therefore, for the matrix addition, we can change the place, or we can say the order of the matrix. But for the subtraction, it is same as algebra. we know that 2 minus 3 is not equal to 3 minus. For the matrix subtraction also, in generally, we can say that A minus B is not equal to B minus A. This is the general rule that we can see for the matrix subtraction. Generally, we can say that A minus B is not equal to B minus A. But there are some situations we can say this equality satisfied. It is because in the final answer, if you are getting zero matrix or a null matrix, then in such situations we can say that these two sides are equal. And simply we can say that if A and B are two equal matrices, the equality exists. Otherwise, in generally we can say that these two quantities are not similar. Therefore, when we are looking for the subtraction of matrices, you cannot change the place of these matrices. It means you cannot change the order of the subtraction that you are considering. Here we have considered matrix A as 2, 4, 1 with 2, 2 by 2 matrix having these elements, and matrix B is supposed to be again a 2 by 2 matrix having the elements as 1, 2, 0, and 4. If you ask to find out the value for A minus B, as the first thing you have to check whether the matrices are in same order or not. If the matrices are in same order, then you can go for the addition subtraction of these two matrices. Otherwise, you cannot go for the subtraction of these two matrices. Then what we can consider here is first check for the matrix, the dimension of the matrices. Here you can see that matrix A has having the dimensions 2 by 2, matrix B also having the dimension as 2 by 2. Now you can see that the dimensions are similar. Therefore, these two matrices are confirmable for matrix subtraction as well. Then what you can do is you can subtract the corresponding elements. Therefore, you are getting these elements as this 2 minus 1, 4 minus 2, 1 minus 0, and 8 minus 4. Then this results the answer as a matrix having the elements 1, 2, 1, 4, having the dimensions 2 by 2. Here also you can see that the order of the or the dimension of the resultant matrix is same as the dimension of the initial matrices considered for the matrix subtraction. Therefore, again, if you go through these wordings, again, it says that for the subtraction of any two matrices, they should be confirmable for matrix subtraction. To check whether the matrices are confirmable for matrix subtraction, you need to check whether the order of these two matrices are equal or not. In the second one, second example, you can see that A has given as a 2 by 3 matrix having these elements, and matrix B is, we'll take this as matrix B, and having the elements with this minus 2, 0, minus 5, minus 3, 4, and 7 with 2 by 3, the order 2 by 3. Then if you ask to find out the matrix subtraction A minus B, here also you cannot change the order. It is because for the subtraction, the general rule is A minus B is not equal to B minus A. Therefore, without changing the places or the orders, then you have to write down these matrices. Therefore, matrix A will come first and matrix B comes later. Since you have checked for the condition for matrices are confirmable for subtraction, here you can see that this is a 2 by 3 matrix and B is also 2 by 3 matrix. Then we can see that the matrices are confirmable for matrix subtraction. Then we can subtract the corresponding elements. Therefore, we will get the values in this form. Here 1 minus minus 2. Then that is why we have written, I have written this in this way. 1 minus minus 2. Then next element would be minus 1 minus 0. Then 3 minus minus 5. Likewise, using this subtraction technique properly, you can obtain these quantities and the final answer gives you a matrix having 2 rows with 3 columns. Here also, if you check for the dimension of the resultant matrix with the initial matrix, dimension of the initial matrices, you can see the dimension of these the resultant matrix with and the initial matrices are equal. And if you consider for this, I will write this example. Suppose that matrix A is given as a 2 by 2 matrix. Suppose that A is given as a 2 by 2 matrix having the elements 1 minus 2, 5 with 0. Then this is a 2 by 2 matrix, and if I take matrix BS and take matrix B this way, if it is 157 with 2 0 and 9, if you are supposed to perform the matrix subtraction A minus B, what you can do is first you need to check whether the matrices are conformable for matrix subtraction or not. Then if you see the value here, you can see that this is a 2 by 3 matrix. Now you can see that the order of first matrix is 2 by 2, but the order of the second matrix is 2 by 3. Since the orders of the matrices are not equal, then the subtraction does not exist. Therefore, we can say that since we can say that the matrices are not conformable for matrix subtraction, the answer does not exist. Now we will move for the next part. It is the multiplication of a matrix by a scalar. If I brief about a scalar is supposed to be a number or just as an integer. Consider a scalar just as an integer. If you have given any matrix and if your matrix is multiplied by an integer or just as an scalar, then what we have to do is we have to multiply all elements of the matrices by the given scalar or the given integer. Simply when you are multiplying a matrix by a scalar, what we have to do is we have to multiply all the elements of this given matrix. And there are another concept called the multiplication of matrices. Multiplication of matrices and multiplication of a matrix by a scalar are two different concepts. Therefore, in the technique of multiplication of a matrix by a scalar, you have to multiply all the elements by the given scalar. But if you are considered for the multiplication of matrices, then it will be quite a different process than this. I will discuss that part laterly. Therefore, if I consider examples from this multiplication of matrix by scalar, we can see that matrix A is given as 1, 5, 3, 8, 1, and 0, having the order as 2 by 2. And if you ask to find out the value for 5 times A, what we have to do is here we can see that 5 is a scalar or it is just an integer, and A is given as a matrix. Therefore, you can perform this multiplication of a matrix by the scalar. Then what you have to do is first you have to write down the scalar and the matrix accordingly, and then you have to multiply each and every element inside this matrix by the given scalar. Here you can see that 5 is the scalar and the matrix is given as a 2 by 3 matrix having the elements as 1, 5, 3, 8, 1, and 0. According to the concept of this multiplication of a matrix by a scalar, we need to multiply each and every elements of this matrix by the given scalar. Then we can see that once you multiply all the elements by this given scalar 5, you can see first elements obtained from 5 into 1, then 5 into 5, 5 into 3, likewise 5 into 8. Here it is 5 into 1 and then 5 into 0. Therefore, if you once you perform this calculation, you will result the matrix as 5, 25, 15, 45, and 0, having the matrix with the order 2 by 3. Since you are multiplying a matrix by a scalar, this does not change the order of the matrix. Therefore, you can see that order of the resultant matrix and the order of the initial matrix are similar. Therefore, once you multiply a matrix by a scalar, the order of matrix will not change. This is one exercise I have included. Therefore, you can try for this exercise by yours. And this comes up to this consists of writing down the order of the matrices, then identification of the conformable pairs for matrix addition and subtraction. Then you have to do some calculation regarding matrix addition, subtraction, and the multiplication of matrix by a scalar. And these are the things that we have discussed so far. Therefore, you can be familiar with the things that we have discussed so far by doing this exercise one. If I move for the next part, and for this session, I will discuss up to the transpose of matrix only, and in the next session, I will discuss about the matrix multiplication. Now we will consider about the transpose of a matrix. If you have given a matrix in the dimension as m by n, it means that if your matrix A has m number of rows, write it in this way. If you are having matrix A having m number of rows and n number of columns, that is why we are getting this as m by n matrix. Therefore, we are saying the order of this matrix is m by n. Then if you are having a transpose of this matrix, generally this is denoted as AT. It is not the a to the power t. This says that the transpose of the matrix A. It says the transpose of the matrix A. If you need to obtain a transpose of any given matrix, what you have to do is you have to convert the rows as columns or vice versa. It means you have to write the rows as columns or else columns as rows. Therefore, what you will get here is you can, according to the definition given, you can see that the number of rows and columns are interchanged. Therefore, the number of columns in this matrix will become the number of rows in the transpose matrix. Therefore, this will be n by m matrix. Therefore, number of columns in the first matrix or the initial matrix becomes the number of rows in the transpose matrix. Then we can obtain this as A transpose is n by M matrix. Therefore, in simply, if you consider the ith row of this initial matrix, if you consider this as the ith row, if this is the ith row of this matrix, then it will become the ith column of the transpose matrix. Then this is equal to the ith column of the transpose matrix. Therefore, this is the scenario behind the transpose of a matrix. If I consider an example on this matter, discussing on the transpose of a matrix, here you can see that A is a matrix having 2 rows and 3 columns, having the elements as 1, 3, 2, 4, 5, and 6. If you're supposed to obtain the transpose of this matrix, what you have to do is you have to write down the rows in this matrix as the columns, or vice versa. It means columns as rows. If we can do it in one way, no need to apply both ways in this matrix. Here we can say that if I am first selecting the rows to write down as columns. Here you can see that in the matrix A, you can see that there are 2 rows. Therefore, if I select the first row 1, 3, and 2, it will become the first column of the transpose matrix. Therefore, first row of the matrix becomes the first column of the transpose matrix. Then we can say that 1, 3, and 2 has become the first column of the transpose matrix. Then here you can see that 4, 5, and 6 in the matrix, initial matrix, then it has become 4, 5, and 6 has become the second row of the transpose matrix. Therefore, now you can see that the columns has switched, the rows has switched as the columns in the transpose matrix. Or if I explain it in this way now think about, this is the first column in this matrix. Now it has become the first row of the transpose matrix. In here, for the initial matrix, the second column has given as 3 and 5. Then second column has become the second row of this matrix. Then this has become 3 and 5. This is the transpose of this matrix. Then 2 and 6, it is the third column. Then it has become the third row of the transpose of matrix. And now you can see that for the initial matrix, the order has given as 2 by 3, but its transpose has become 3 and 2. That's why I have initially said that the rows are interchanged with columns. Therefore, number of rows will be changed or converted into number of columns, and number of columns will be converted into number of rows in the transpose of a matrix. Using the concept of transpose of matrix, we are defining the symmetricity of any given matrix. Suppose that matrix and a transpose of that matrix are equal matrices. Now you can see that the concept of equality of two matrices is used. Therefore, if you can see that the matrix and its transpose are equal, then we are saying that those two matrices are equal matrices. Here you can see that the symmetricity of a matrix, it is only for the square matrices. But for any other matrices, you can obtain the transpose, but you cannot see any symmetricity there. It is because symmetricity is only defined for square matrices only. If you go through these examples here, you can see that B has defined as a 3 by 2 matrix, not a square matrix. Then you can see that its transpose has obtained, can obtain a transpose. Then 2, 4. First row becomes the first column. Second row becomes the second column. Third row becomes the third column. That is how we are getting B and transpose of B in this form. But if you move for the matrix C, C is a row matrix. Then if you take the transpose of this row matrix, then you can see it as a column matrix. For the matrix D, if you are considering matrix D, D is a column matrix. You can see that there is only one column. Since you can see that there is only one column, its transpose is considered as a row matrix. Therefore, this is how we are obtaining the transpose of a matrix. Then if you are getting the these two examples, here you can see that A is given as a 2 by 2 matrix, and if I write it here, matrix A is given as 2, 3, 3 and 1. Here you can see that this is a 2 by 2 matrix. And if you take the transpose of this matrix, you can get the transpose of this matrix. First row becomes the first column. The first row elements are 2 and 3. Then it becomes first column of the transpose matrix. Then here you can see that the second row elements are given as 3 and 1. Then this will become the second column elements. Therefore, here you can see that this is also a 2 by 2 matrix. Then we can say that here it is 2, 3, 3 and 1. We can say that these are two equal matrices. It is because number of rows are same, number of columns are same, and here you can see that the corresponding elements are also equal to each other. Therefore, you can say that A and you can say that matrix A and its transpose are equal matrices. Therefore, we can say that A is a symmetric matrix. Now you can see that A is a square matrix That is why we can think about the symmetricity, but each and every square matrix is not a symmetric matrix. But if you consider in the other way around, it means that if you consider any symmetric matrix, it should be a square matrix. For the next example also, if you are considering the second example, 1 4 3 4 0 5 and 3 5 2, if you take the transpose of this matrix B, if I directly write down the transpose of this matrix B transpose, the first column will become the first row becomes the first column. Therefore, the first row is 1 4 and 3. It will become the first column of this matrix. It is now 1 4 and 3. Then second row, it is 4 0 5. Then it will becomes the second column of this matrix. It is now 4 0 and 5. Then third row becomes the third column. It is 3 5 and 2. Now we can see that if you are considering this matrix, this is also a 3 by 3 matrix. Now if you compare the corresponding elements, since you don't need to check, it is because as we see these two matrices, we can see number of rows and number of columns are equal, number of rows same, number of columns same. Then if you see about these the corresponding elements, you can see that all the corresponding elements are similar in between this matrix B and the transpose matrix. Therefore you can say that matrix B and its transpose are equal matrices. Therefore you can say that B equals to transpose of B. Then we can say that B is a symmetric matrix. That's why we can say that B is a symmetric matrix. And again, I would like to say that these symmetric matrix are only defined for the square matrices. And if you see about the main diagonal, suppose that if you are following the symmetric matrices along with the main diagonal, you can see that the coinciding elements are similar. It is because here 4 with 4, it is similar. Here 3 with 3, again it is similar. 5 with 5, again it is similar. It is because if you are folding this matrix along with the main diagonal, you can see that the coinciding elements are similar. And this is all I'm discussing for this session, and I will discuss about the matrix multiplication and furthermore theories related with matrices in the next session. And thank you all for participating with this session.